bit of this on your own, but we'll go through some of these problems anyways. Basically what we're going to try and do is use differential equations to write some tangent lines, to determine whether things are maxes and mins, to find the second derivative. There's a few things that are slightly, that does not work, but it's kind of working. Okay, good luck. So let's jump in, shall we? Okay, we've got this differential equation. We've got a particular solution to this differential equation, write an equation for the line tangent to the graph of y equals f of x equals 1. Well, what do you need for a tangent line? You need a slope and you need a point, right? Because this is our tangent line equation, y minus f of a is equal to f prime of a times x minus a. That's basically your tangent line equation. Morning.
Good morning.
Hello, Will.
Hello. Did you get my email?
No.
Okay, sounds good. I didn't send one.
Hi, Andrea.
Okay, I did send an email.
Classic. Yeah. Don't hit the recording here. That's my
Okay.
coffee and
Is that for Ariel?
recording for Ariel.
As loud as voices.
So in any case, we want to write the tangent line. We need a point and we need a slope. They gave us a point, which was 1, 2. And we can find the slope by plugging 1, 2 into our differential equation, right? To find our slope. So we can just do that. dy dx evaluated at 1, 2. This is going to allow us to find our slope at 1, 2. Right? You got a pencil in there? Really? Wow. So if we plug 1, 2 into our differential equation, that's going to allow us to get our slope, right, at that point, because this is literally just the slope, dy dx. So if we plug in 1, 2, we get 1 minus 1 over 2, which is 0. So that means the slope of whatever this curve is at that point is just 0, which means what kind of line are we dealing with? It's, who knows? Are we awake? It's a horizontal line, right? Because the slope is 0. So essentially what that tells us is that the equation of the tangent line would just be y equals 2, because it's a horizontal line, right? If you ever want to find the equation of a tangent line, you need a point, you need a slope. They gave us the point, which was 1, 2. How do you find the slope? You use your differential equation, because this is saying that dy dx is equal to this, so you can just plug in your point and get your slope, and now you have your tangent line. If we actually use this whole tangent line equation, we would get y minus 2 equals 0 times x minus 1. But it's somewhat obvious that that just simplifies to y equals 2. So we have our tangent line. Great. Okay, let's find d2y. Let's find the second derivative, d2y dx squared, in terms of x and y. So we are now going to take the derivative of x minus 1 over y. What is the big rule that we're going to have to use if we want to take this derivative? The quotient rule, because that's a quotient. The quotient rule says low d high minus high d low over the denominator squared or something like that. So we're going to go ahead and do that. Low d high, what's the derivative of x minus 1 with respect to x? 1, so it's y times 1 minus high d low, so that would be x minus 1 in parentheses times the derivative of y. What's the derivative of y with respect to x? dy dx, right? Because we're taking the derivative implicitly, right? So y is not a variable. We're not just going to get 1. It's a function, so the derivative is dy dx. And then that would all be over the denominator squared, which is y squared. So that's the derivative, but it's not in terms of x and y, because we have this dy dx in here. But what we can do is, since this is dy dx, we should be able to substitute that in for dy dx here, and then we can write our entire second derivative in terms of x and y, instead of having it also depend on dy dx. So from there, we can then say d2y dx squared, the second derivative, is equal to y minus x minus 1 times dy dx, but remember dy dx is just x minus 1 over y, all over y squared. That's now the second derivative in terms of x and y. So when you take a second derivative of these differential equations, you're going to end up with a dy dx that you're then going to substitute back in so that you can write your second derivative only in terms of y and x. You didn't believe it? All right, friends. So the next question says, let y equals f of x be this particular solution with initial condition f of 1 equals 2. Does f have a relative min, max, or neither at x equals 1? Remember, if you want to show whether something has a relative min or max, you have two possibilities. You can use the first derivative test, or you can use the second derivative test. First derivative test does not work with differential equations because you have the x and the y. So are you moving up and left? Are you moving up and right? Are you moving down and right, down and left? There's no way to use the first derivative test if you have both an x and y, because you can't just move left and right because of the y value. So that means we need to use the second derivative test.
Does that not also use the y value?
But the second derivative test, you don't look left and right. You just plug in a value and see whether it's concave down or concave up, right?
Oh.
So second derivative test, remember, I'll just remind you, says if dy dx equals 0, and the second derivative, d2y dx squared, is greater than 0, then we can make a conclusion. If the slope is 0 and the second derivative is positive, that looks like this, right? 0 with positive concavity, which gives us a minimum. You remember the second derivative test? Maybe?
Yes.
If not, that's fine, because I didn't teach it to you. And then if the slope is 0 and the second derivative is negative, that looks like this. So that gives you a maximum, right? So that's just a reminder of the second derivative test. So we basically need to check at this point, is our slope 0? And is the second derivative positive or negative? So let's do that. Okay, step 1, let's see what dy dx is at this point, which I actually think we already know, right? dy dx evaluated at 1, 2 was 1 minus 1 over 2, which is 0. So that's good. That means we have a horizontal tangent. So it's a candidate, right? It's a critical point. It's a candidate for a max or a min. Hey, son, good morning.
Good morning.
Oh.
How are you?
I'm doing quite well. How about you?
I'm fine.
Say hi to Benson.
Hi, Benson.
Oh.
Oh, hi,
Wait,
Benson.
don't try the camera.
Such a disruption.
Okay, next up, friends, we need to check and see what the value of our second derivative is at this point. If it's positive, we're going to have a minimum. If it's negative, we're going to have a max. If it's 0, then we don't know what's going on. So let's go ahead and plug this into our second derivative. We get 2 minus 1 minus 1 times 1 minus 1 over 2, all divided by 2 squared. This whole thing right here goes to 0, because 1 minus 1 is 0. So we just get 2 over 4, which is 1/2. We don't really care what the value is. What we care is that that's positive. That's greater than 0. So that's giving us this scenario, right? Our slope is 0, so we have a horizontal tangent, and it's concave up. So is this a max or a min, or neither? Unknown. There is a max value at 1, 2 cents. dy dx evaluated at 1, 2 equals 0, and d2y dx squared evaluated at 1, 2 is greater than 0. Right, that's the second derivative test. If you have your slope being 0 and your concavity being up, second derivative positive, then you end up with a min. Am I right? Min? Is it a min?
Yeah.
Okay, min. There we go. Minimum value. You guys are good? Hey, son, don't worry about catching up because the other two problems are very similar. So I would just focus on what we're doing now and it's the second problem. Okay. Okay, great. Find the particular solutions. This is a review. For most of us, maybe Inray and Manola missed it. So we can review finding the particular solution. Let's just get a new thing right here. So remember, this is separation of variables, which I find to be kind of fun. dy dx equals x minus 1 over y. Remember, if you want to find a particular solution, you're going to separate your variables and integrate both sides and use your initial condition to find your c value. So I'm going to multiply both sides by y, multiply both sides by dx, and I should get y dy is equal to x minus 1 all times dx. That's the separation of variables. I'm treating this like a fraction, multiplying both sides by dx to move the dx over, multiplying both sides by y to get the y over, and now I have all my y's on one side and all my x's on the other. Right? Just stick a couple of extra steps for the benefit of people that were gone. In any case, you get this. Now I'm going to integrate both sides. So the integral of y dy is y squared over 2. And the integral of x minus 1 is x squared over 2 minus x plus c. So I separate my variables and integrate both sides. Y squared over 2 equals x squared over 2 minus x plus c.
Wait, so you multiplied, okay, by dx and y?
By dx. Yeah, y dx basically. I'm going to multiply everything by 2 because I'd like to, and I get y squared equals x squared minus 2x plus c. Remember that I don't really need to write 2c because c absorbs that too. It's just a random constant, so I don't need to write 2c. I can just write c. What was my initial condition? What was my point? Is it 1, 2? F of 1 equals 2. So now I can plug in this point in order to find my c value. Plug in 2 for y. I'm going to get 4 equals 1 minus 2 plus c. So I think that gives me 5 equals c. So that's my c value of 5. So plugging that in, I end up with y squared equals x squared minus 2x plus 5. And now I just need to solve for y. So I get y equals plus or minus the square root of x squared minus 2x plus 5. Thumbs up if we're going to choose the plus. Thumbs down if we're going to choose the minus. We have to choose one of these because it's a particular solution. Thumbs up if we're choosing the plus. Thumbs down if we're choosing the minus. I'm seeing mostly thumbs up, and you're right. We're going to choose the plus because we need the y value to be positive too. So we can't choose the minus here because when we plug in 1, we have to get positive 2. And so that's why we're going to choose the positive one of these. Y equals the square root of x squared minus 2x plus 5. And that would be my particular solution there.
What?
Right? Questions? Are we awake? Sort of. Are we just being super quiet because we don't want our voices to be recorded for Ariel?
You don't want to distract them.
You don't distract
Who's
Benson.
Ariel?
Benson's currently at Robotics Worlds. You should be kind to Benson.
Wait, didn't Benson already win?
Because she may rule the world one day. You're gonna be kind.
There's no may about it.
Where's he going?
Who do you think in this room is most likely to be my boss in the future?
Benson?
Benson?
Probably
No,
Isaac.
Benson isn't this week.
Maybe Benjamin? I could see Benjamin being like head of school, being like, oh, you gotta be kind to the students, man. You're right. Did you have a good trip, Henry? You went to Japan?
Wait, I did
How about you and
too.
Alana?
Great. Okay.
Colombia?
Great.
Great.
Yes.
That's good. One of my friends is getting married in Colombia. So I think I might get to go.
Put on a little accent for us there.
Colombia? Sara Garcia? Sarah? Anyways, okay, should we move on to the next problem? I think so.
Next one.
Let's
Oh,
do
sorry.
it.
Sorry. I was just in Mexico.
That's pretty much it. All right, let's see some new things. Here's our differential equation. dy dx equals xy cubed. Okay, particular solution, blah, 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 same point, f of 1 equals 2. Write an equation for the line tangent to the graph of y equals f of x at x equals 1. Well, we definitely need the slope, so we better find the slope evaluated at that point.
No
Right?
way.
Because that's how we find the slope of the tangent line. We use the derivative, which is dy dx. So we plug in 1, 2. We get 1 times 2 cubed, which is 8. So there's our slope of the tangent line, right? Just plugging in 1, 2. We have our slope. That's our slope. And we have our point. And our point is point 1, 2. So we have a point, we have a slope. We can just do y minus y1 equals m times x minus x1. Done. Boom. Tangent line at that point, we're done. Right? Y minus the y value equals the slope times that. We might want to write it in, sometimes it's nice to have it in slope-intercept form, so we'll write y equals 8x minus 6 would be another way to write it. That's now in slope-intercept form. Y equals 8x minus 6.
Wait, where did you get this? Did you get?
Just simplify
Where did you get?
Do you agree with the minus 6 or not? Maybe, possibly, no?
Wait, is this the y minus f of a equals f prime of a times?
Yeah, I
x
mean,
minus a?
remember, the equation of the line is y minus y1 equals m times x minus x1, right? That's the, I think, one of the most useful forms of a line, point slope form, but in calculus notation or function notation, we write f y minus f of a equals f prime of a times x minus a. That's the same thing. That's just point slope form. One of them written in Algebra 2 land and one of them written in calculus land. But I mean, that's just writing the equation of the line. Use the tangent line to approximate f of 1.1. So f of 1.1 should be approximately equal to y of 1.1. So if we plug 1.1 in here, we get 8 times 1.1 minus 6. Right? Remember that we have some function, we have a tangent line at a point, and now we're plugging into the tangent line to approximate the function value. That's what's going on when you're approximating a function with a tangent line. Some function, you found the tangent line at the point 1, 2, and now you're plugging in 1.1 because it should be a decent approximation if you're not too far from that. Just a reminder what a tangent line approximation is. 8 times 1.1 is something like 8.8 probably. Is it? Minus 6 is 2.8. Done. So we approximated our function value by using that. Not saying necessarily this is easy, but this is all review of things you've done before.
What?
So that's why I'm moving through at a reasonable pace here. Okay, shall we find the second derivative?
Yes!
What rule are we going to have to use with the second derivative?
That one rule.
That one rule.
Second. Wow.
You good, Nina?
No.
Product rule says Grant.
Wait, we
Nice. Product rule.
Oh.
d2y dx squared. Friends, the product rule says first derivative second plus second derivative first, right?
It's actually
So,
just so much more calm without
first-
pence in here.
Derivative second. What's the derivative of y cubed? The derivative of y cubed, Nason, is 3y squared times dy dx, right? This is implicit differentiation,
What?
which is also review.
Whoa, 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 wait,
Y as a function inside x cubed, you take the derivative of the outer function, which is blob cubed, and you get 3 blobs squared, but you also have to multiply by the derivative of the blob, which is dy dx.
Wait.
First, derivative second. Do we need an implicit differentiation? Pause.
Wait. Wait, is it? Whoa. So wait.
As an aside, friends, some of you need this, some of you maybe don't, that's fine. When we have something like y squared plus 2x equals 10, and we want to take the derivative of this, right? Take the derivative of each piece. This, remember, when we take that derivative, y squared, that's a function of x right there. So the outer function is the squared function, and the inner function is the y function. The chain rule says you need to take the derivative of the outer function and then multiply by the derivative of the inner function. Anytime you take the derivative with respect to x of y, you have to multiply by dy dx. That's the chain rule. That would be the same as if we took the derivative of sine x squared, right? What's the derivative of sine x squared? You take the derivative. You take the derivative of the outer function, leave the inner function alone, and then what do you have to multiply by? You have to multiply by the derivative of the inner function, which is cosine x. That's the exact same thing.
Are you expecting something?
Nathan, are you expecting?
Oh, really?
Wait, what's your bean?
We have fake, like, funny.
Wait, with who?
Well, he told me my haircut was garbage.
Oh my god.
You should bring him in here, settle it.
Alvin, you should start calling him Soak.
Okay.
That's what he's called now.
Okay, so friends, that's implicit differentiation.
That's by me.
And we need to finish this problem. First derivative second plus second times the derivative of the first. What's the derivative of x? Any ideas?
Wait, so is it just
Which one?
derivative of one times the other, and then derivative of the other times the one?
Yeah, right? That's the product rule? Oh
God.
my god. Derivative of the product rule is fg prime plus gf prime, basically, right? First derivative second plus second derivative first. That's the product rule. Boom, we got dy dx. Oh, we got d2y dx. Is it in terms of x and y? It is not. So at that point, you should take whatever dy dx is and substitute it in for dy dx to make sure that you're writing it only in terms of x and y. So now we can say that the second derivative of y with respect to x, d2y dx squared, is equal to x times 3y squared times xy cubed equals y cubed. Nice simplification. We'll say 3x squared y to the fifth
What?
plus y cubed. That would be our second derivative in terms of x and y, right? Maybe? Possibly? Did I simplify correctly?
Wait.
I think so.
Oh wait, we know dy
dx. For dy dx.
You solved it on your paper.
And then I'm just simplifying.
Sorry.
So there's my second derivative in terms of x and y. In general, friends, how do you find the second derivative? You take the derivative implicitly, and then you need to substitute dy dx back in so that it's in terms of x and y. What does it ask us to do next, I wonder?
Is it an overestimate or underestimate?
Okay, how do we tell whether a tangent line is an over or underestimate? If it's like this, it's an underestimate. If it's like this, it's an overestimate, right? So we need to look at the concavity. We need to look at the second derivative to see whether the function is concave down, in which case our tangent line approximation is on top, it's an overestimate, or concave up, in which case it's going to be an underestimate. So we need to find the second derivative at that point. And the point was 1, 2. When we plug 1, 2 in this, we're going to get some random number which I don't care about. Is it going to be positive or negative?
Positive.
It's going to be positive. That's all I care. It's going to be a positive number which is greater than 0. I don't care what the number actually is. I just care that it's positive or negative. So easy to see this positive. Boom, I'm just going to say it's positive. So what does that tell me? That tells me I'm dealing with this scenario. That's the point 1, 2. So when I find the value 1.1, you can see that that's an under approximation. So I could say something like, this is an under approximation.
Wait. Wouldn't it?
Since f of x is concave up. Right, the function's curving up, your tangent line is underneath. So again, we're using the second derivative to now show that that's an under approximation. Oh, and now I get to find the particular solution. Yay, my favorite part.
Why do you like the particular solution the best?
I don't know, it's just like
Why
easy and very algebraic, and I kind of like algebra. Shall we find the particular solution to this bad boy? Of course. dy dx equals xy cubed. Okay, we need to separate the variables, which means the dx needs to come over onto the other side. We'd have dy equals x dx times y cubed.
What?
So I got the dx over onto the other side. I'm just taking more steps than I necessarily need to, but I got the dx over onto the other side. Now I need to divide the y cubed over, so I'm going to have dy over y cubed is equal to x dx. So now I have my variables separated. Lovely. Just divide by y cubed. But I don't want y cubed in the denominator, so I'm going to rewrite it as y to the negative 3, because that is easier to anti-differentiate. Y to the negative 3 dy equals x dx, right? No problems. Integrate both sides. Bada bing, bada boom, like so. Lovely. Power rule. Y to the negative 2 divided by negative 2 is equal to x squared over 2 plus c. A reminder, you don't need to add plus c on both sides, because then you could just subtract that c over here and combine them together. So you only need to add plus c on the x side.
Can we multiply by 2
Let's multiply by negative 2.
or negative 2?
And let's get y to the negative 2 equals negative x squared plus c. Again, remember, c can absorb things. So c absorbs the negative 2. And now we have a reasonably simple equation. We got to find c. So what was the point? 1 comma 2. Let's plug it in. 2 to the negative 2 equals negative 1 plus c. 2 to the negative 2 is 1/4. And that equals negative 1 plus c. Add 1 and you get 5/4 is equal to your c value, I think, if you plug in 1, 2. There's, always slightly different ways to do this. So you may have done it differently and gotten a different c value, but ultimately you're going to end up with the same thing. Is that thing still rolling?
Indubitably.
I don't know what kind of, I did delete a bunch of pictures recently, so.
I forgive you.
Ay, ay, ay. Okay.
That's a bunch of pictures, just like your first order video for fencing.
No, I was just bored on the plane. Okay, so now I have this equation, but I do need to solve for y. There are different ways to do this, but I'm going to make these into a fraction. So I'm going to write this as 1 over y squared equals, there, ow, ouch, 5 minus 4x squared over 4.
Nothing.
Well, you messing with that?
No.
Do you agree that this side, the right-hand side of the equation, is the same thing? Yeah. I just got a common denominator, reverse the order. Those are the same thing. Now I can basically flip both fractions, blah, like so, and get y squared is equal to 4 over 5 minus 4x squared. You can just flip both of those, because you just have a fraction equals a fraction, so if you have a proportion, you can just use that. Take a square root. Y equals plus or minus
Why we
square
do all
root
that?
4 over 5 minus 4x squared. Are we going to choose the plus or the minus here? Plus, 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 plus. Y equals square root of 4 over 5 minus 4x squared, or probably better to write 2 over the square root of 5 minus 4x squared.
Can we just take
Oh wait, yeah.
do like the right side to the negative 1/2?
Sure, but what does that mean?
Like we get to skip all those steps.
Maybe, but do you actually know what raising something to the negative 1/2 means?
Yeah.
Yeah.
Okay, what does it mean?
Taking the but it's on the underside of it.
Okay, did you do a plus or minus when you did that?
I haven't done it yet.
Okay, would you though?
I'm still theorizing.
Would you do a plus or minus?
Well, You would, and then you would make it just plus.
Okay. Yeah, sure. There's other ways to do this. Your way might be faster, might be better. So you should do the faster, better method would be my suggestion. That might be yours. Might be mine. I don't know. Different ways to do it for sure. Okay, now you are going to work on the last problem while I print your homework. Sounds good? Now, don't get too confused about R. R is just Y. And T is just X. So remember that R is just Y. I'm going to print your homework, then I'll come up and check and see how that problem went. And then we'll start working on that homework. Let's see if I can print this. And let's stop this. Bye.
Bye, Benson.